Ready to get started. I'm going to be your moderator this afternoon. And thank you for joining us today on the call to learn about what is emissivity, reflectivity, and how do they affect infrared temperature reading. Our presenter today is Ed Kochanek with FLIR Systems. Ed is the Regional Sales Director at FLIR. He has been working with customers on their thermal imaging camera needs for his over 14-year tenure at FLIR. He is a certified thermographer, having received his certification through FLIR's Infrared Training Center. More thermographers have been trained at FLIR's Infrared Training Center than at any other training organization in the world combined. Today we'll spend the first part of our time in presentation, and we will end the call answering your questions. During any time of the presentation, you can send questions through the question box to the right in your webinar controls. I also want to mention that this webinar is being recorded. Each of you will receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. So at this time, I'm going to turn the presentation over to Ed.
Good afternoon, everybody. Thank you for stopping by. Nicole, if you can make me, thank you.
There you go.
Okay. All right, we're good. All right, well, good day and welcome. It is my pleasure to present this webinar on behalf of Transcat and FLIR Systems. We appreciate you taking time out of your schedules to meet with us for the next 30 to 40 minutes discussing emissivity and the potential impacts this property may have when making thermal measurements with an IR camera. The agenda for today's webinar is as follows. First, I will address what it means to measure temperature with the measurement technologies available today. Then I will review some general infrared theory. I will then review the definition of emissivity and reflected radiation. Following this, I will demonstrate some of the methods used to work with emissivity that produce accurate quantitative results. And in closing, I will summarize our findings. I will point out that the subject of emissivity is an extensive one, and for thermal imaging and measurement applications is covered over days in American Society of Non-Destructive Testing, or ASNT, certified training courses. The content presented today is but a brief glimpse into the emissivity theory and how to compensate for reflected radiation interference. So let's get started. First of all, do you realize there is no direct method to measure the absolute temperature? All temperature measuring devices report or calculate a temperature value based by measuring an effective temperature. For example, a thermistor measures changes in resistance associated with changes in temperature. A thermometer measures changes in volume associated with changes in temperature. A thermocouple measures changes in voltage associated with changes in temperature. IR thermometers also measure changes in voltage associated with changes in temperature. In an infrared camera, more specifically, the camera we will use today measures changes in resistance associated with changes in temperature. All of these instruments report a temperature value based on the measurement of some other parameter. For today's presentation, we will focus on IR cameras only. Let's discuss how IR cameras see infrared radiation and report a temperature value. Let's first look at temperature, the operation of an IR camera. In this example, we are referencing the FLIR T420. This camera has an uncooled microbolometer focal plane array infrared detector. A microbolometer is a thermal-based sensor, meaning it produces a resistance change when heated. Our focal plane array contains 76,000 detector elements, each element being a single bolometer. With the lens of our camera, we focus infrared radiation onto the detector elements. As the radiation strikes our elements, they heat up and the respective resistance changes. Using a readout integrated circuit, we can measure the resistance medium increases, so does the molecular movement in collisions. Thus, an increase in temperature produces an increase in the release of photons. This form of heat transfer caused by the release of photons is known as thermal radiation or infrared radiation. Thermal or infrared radiation is what is sensed or seen by an IR camera. The chart here shown is a representation of the electromagnetic spectrum. From the chart, we see how infrared of interest. The apparent temperature is the temperature value reported by our IR camera. I say reported temperature value and not measured value because, as you remember, our IR camera does not measure temperature. Our camera measures the effective temperature, performs some mathematical calculations related to a calibration procedure, and then reports a temperature value. Our goal in using IR cameras is to try and make the reported apparent temperatures be as close as possible to the accurate actual temperature of the target. In reality, the objects we are likely to measure are not perfect radiators or black bodies. Our targets will have emissivity values less than 1. As such, the total radiation reaching the IR camera could be a combination of emitted, transmitted, and reflected radiation. Transmitted radiation from a source in front of the target that reflects off the target surface, like seeing your image reflected off the surface of a mirror. The temperatures associated with the reflected radiation is known as the reflected apparent temperature. It is also known as T reflected or T background. The IR camera sees the total radiation from the target of interest. It cannot differentiate between the various sources of radiation on its own. It is the camera user who must tell the instrument what makes up the total radiation so the instrument can calculate and report an apparent temperature close to the actual temperature. Let's discuss further the potential impact reflected IR actual temperature. Think of like pouring 25 parts of 0°C cold water into 75 parts of 40° water. Similar to the cold water diluting the warm water, reducing the temperature. The cold or reflected radiation will dilute the warm radiation emitted from the target surface. Now let's say the temperature of my target of interest is 40°C, and the source of the reflection is a large fire with a temperature of 500°C. Once again, I have done nothing to the IR camera to compensate for emissivity. Will the camera report an apparent temperature higher or lower than the actual temperature? Third, we see that emissivity can vary by wavelength. Look again at the rough aluminum. We see that there are different emissivity values for the mid-wave IR spectrum at 3 microns and the long-wave IR spectrum at 10 microns. Finally, from the table, we see that emissivity values listed at specific temperatures, indicating emissivity can vary for a given material with changes in temperature. In summary, we've learned that from a study of the emissivity table that emissivities can vary with material, surface, roughness, wavelength, and temperature. Additionally, emissivity can vary with camera viewing angle to the target and the target surface geometry. But what if you cannot find your material in a table? Or what if you're requiring to know your specific emissivity for your specific conditions? There are methods available for determining emissivity. We will uncover some of these in a demonstration that follows. My demonstration for today is quite simple. I will image and measure the pouring of hot water into a stainless steel cup. I will use a thermocouple placed inside the water in the cup as a comparison reference for the IR camera. In my demonstration today, I will use the following equipment: a FLIR T420 thermal camera, an X-Tech Type K thermocouple, a stainless steel cup, Scotch 3M black electrical tape, and foot powder spray. Let's first take a look at our stainless steel cup at steady state with no fluid in it. The IR image presented here with its corresponding color palette and temperature scale would lead you to believe that there is a temperature variation across the stainless steel cup. Additionally, the line 1 region of interest and corresponding line profile also indicate variations in temperature across the stainless steel cup of almost 10 degrees. That's right. This stainless steel cup, it appears that there are a 10-degree difference across it. Unfortunately, this apparent variation is a lie. In reality, there is no thermal variation across the surface of our stainless steel cup. The apparent variations are a direct effect of low emissivity and reflected radiation. As a general rule, targets with low emissivities below 0.5 are are difficult to measure, and targets with very low emissivity below 0.2 are very difficult and sometimes impossible to measure. Making measurements on low emissivity targets. First, anything that can be done to reduce the surface reflectivity, like applying a surface coating or roughening of the surface, will improve measurement accuracy. Second, you can look at the geometry of the target too. Third, adjusting the camera to target viewing angle or controlling the imaging environment can Let's explore these correction methods in more detail. First of all, let's discuss coatings. There are primarily two categories of coatings, temporary and permanent. Listed here are various temporary and permanent coatings with high emissivities of 0.95. Remember, this means 95% of the radiation from these coatings will be emitted, while only 5% will be reflected. Let's return to my stainless steel cup demo. To improve my imaging and measurement results, I will apply two temporary coatings, 3M electrical tape and a strip of foot powder spray. From the emissivity tables, I know my 3M electrical tape has an emissivity of 0.95. I am not certain of the emissivity value of the foot powder. However, I do know from a visible perspective that the foot powder is less reflective than stainless steel, and generally it should be less reflective in the IR spectrum. There are methods available for determining unknown emissivity values. I will show you how this is done. But first, just as important as knowing the emissivity of our target for accurate measurement is the need Let's first look at our demonstration with no emissivity correction applied. I will record a thermal movie file of pouring the hot water into the stainless steel cup. From that movie file, I will apply regions of interest or analysis tools to report average temperatures values of the foot powder, stainless steel, 3M, tape, and aluminum foil surfaces. The plot in this slide, generated from the analysis software, represents a temperature versus time plot from 4 regions of interest. The brown line shows the apparent reflected temperature measurement, which appears to be fairly constant. The green, blue, and red lines represent the stainless steel, 3M tape, and foot powder temperature measurements, respectively. From the chart, we see that the 3M tape and the foot powder coatings produce fairly accurate results without any emissivity correction when compared to the internal thermocouple temperature of 51 degrees C. The measurement from the stainless steel surface, however, varies dramatically from the internal thermocouple measurement, with a difference of more than 25 degrees. Let's see how we can improve these measurements through emissivity correction. There are methods for doing this. And 0.5% reflective. The plot shows the corrected calculated temperature tracks almost exactly with the 3M tape. Speaking of 3M tape, I did use a calculator to generate an emissivity value to check against the table value. The calculator results match the table perfectly at 0.95. Finally, let's look at the stainless steel. The emissivity calculator generated an emissivity of 0.099, or in other words, the stainless steel cup is a terrible emitter. But even with such a low emissivity value, with the corrections applied, the reported temperature tracks closely with the tape and powder coating measurements. Here's another example of how you can mitigate the forces of emissivity. This is a picture of a hot iron. Spot 1 measures 97 degrees. We know that the iron is much hotter than that. When we put a spot on the steam holes, we get a reading much closer to the truth. Spot 2 measures 259 degrees. So why the difference? The way this factor works is that cavities, angles, and holes will all start to resemble the way a black body simulator is designed. PCB exposed to the environment of the lab. As you can see, there are considerable color variations or apparent temperatures across the board. The variation is the result of reflected radiation. The bottom right thermal image was taken of the PCB when the IR camera to target angle varied slightly. This shows a substantial reduction in color variation or apparent temperature variation. As long as I stay within 40 to 45 degrees normal length, temperature, camera viewing angle, and target surface geometry. Coatings, surface roughness, camera software, viewing angles, environment, and geometry are methods available for working with emissivity and reflection of interferences. IR cameras are great tools for non-contact temperature measurement. The thermal image combined with several measurement spots takes the guesswork out of the thermal analysis. The subject of emissivity and reflectivity is covered more. So that ends the educational part of the presentation. I would just like to touch on a little bit about what camera is right for you, and just to do a brief overview of what other cameras are available out in the marketplace today. So what are the questions you should ask? How far from the target are you? How hot is the target? What other applications would you use the camera for? How often will you use the camera? What camera features do you need? Who will use the camera or cameras? And what type of reporting or trending will you do? Historically, our cameras have been very expensive, difficult to use, bulky to carry, and required extensive training. But the cameras today have gotten much simpler, and in that case, much more affordable. Just recently, we've introduced the new FLIR EX series. The EX series is our groundbreaking thermal imaging camera that starts at $995 and goes up to $5,995. It has a radiometric JPEG image storage. It has our new multispectral imaging technology where we are applying the visual and thermal in an augmented state to apply tremendous IR definition. It is focus-free. It has a 3-inch color LCD. It measures up to 250 degrees C or 432 Fahrenheit and has pixel range from 4,800 pixels to 76,000. our presentation today. I will open up the webinar for questions, but as you can see, we have the 800 number or the 585 number for Transcat, and you can email them at sales@transcat.com. Again, thank you, Nicole.
Okay, so right now we're open for questions, so if you do have a question, please type it into the question box on your webinar panel. But I'll start with the first question. How far away can you measure a target with a thermal camera?
That's a very good and basic question, Nicole. It really depends on the size of your target and in relationship to the number of pixels. Generally, a camera that has 76,800 pixels can accurately measure a 1-inch target from about 20 feet away. If you cut the number of pixels in half, you generally can cut the distance in half. If you are twice as far away, then you would have to increase the number of pixels, let's say up to 307,000 pixels to get that same 1-inch target. So really, it depends on the size of the target that you wish to measure. And ultimately, you would like to have a minimum of 3 pixels across your target. You would like to have a 3 by 3 pixels, so you would have 9 pixels on your target size. And the fine people at Transcat and FLIR can help you select the right camera.
Okay.
Any other questions?
Yeah, we have quite a few that have come in.
Excellent.
I'll go to the second one. What is the smallest target you can measure?
The thermal cameras have the ability to measure very, very small targets. For example, we have standard optics that can get down to 25 microns in spot size. 25 microns in spot size is 0.025 millimeters. So that is a very small spot that you can measure. We also have cameras that can get down to 10 microns or 0.010 millimeters. Again, these are very high-end cameras, but nonetheless, we can get down to very small targets easily with our thermal imaging cameras.
Okay. Let me see. This one's regarding the T400.
Uh-huh.
Okay, so it's someone who is a current customer. I purchased the T400, and it's good, but I find I tend to measure electronics, which don't vary much from ambient temps, and I feel like the thermal resolution is not fine enough in this camera. I'm missing a small difference in temperature. Are there settings I should be changing, or did I pick the wrong camera?
Well, your camera has 76,800 pixels. You can get optics. I had just mentioned you can go down to 25 microns. FLIR makes an optic that goes down to 25 microns or 0.025 millimeters. So optically, it can get to a very small target. There's another way to look at it is sensitivity. Sensitivity is the ability for the T400 to resolve subtle temperature differences. I believe the T400 had a sensitivity of 0.07 degrees C. So there are other cameras out on the marketplace that go far below that. And there's also software involved that if you invest in some of our other software programs, you can get other features like image subtraction that will really help you identify the subtle temperature differences. Those would be questions that you should explore with Transcat and the FLIR salesperson in your area as we can help out. But there are other cameras that can get down to 3 times the sensitivity today on the market that could really find those subtle differences, and those cameras are very affordable compared to where cameras were priced 3 and 5 years ago. So now is the time to consider looking at even higher end cameras if you have the ability or budget for it.
Okay. We have several, so I'm going to go through. We have a couple good ones in here. So what is the best emissivity setting when viewing electrical distribution equipment which contains many different materials and forms?
The best emissivity, again, is, as we described, you really should look at, if it's shiny, then you're going to have a problem. You're going to have to correct for it. I've known customers in doing electrical work, when it's the end, wrap it around the bus bar or an electrical item. But also, you can find many cavities as well. As we described, the cavities act almost like a perfect emitter. So that gives you the ability to artificially raise the emissivity and get a good temperature measurement. Unfortunately, there's no set good emissivity value since you have so many different materials or different shininess. But if it's weathered, if it's oxidized, meaning if it's been outdoors, that would always raise the emissivity. But there's no rule of thumb of what's a good emissivity. Now, I've noticed many consultants and people out there set the emissivity default to 0.9 as a general rule of thumb or point of reference. Cameras have anti-reflective coatings, so reflected radiation from outside of the field of view gets cut off before it even gets to the detector. So visible light has no influence on what the thermal camera can see or measure. So you should be fine in any LED design or chip or anything where that light is being emitted into the camera. That light is not reaching the detector.
Okay. Here's another. We probably have 3 or 4 more to go.
That's fine.
And they're still coming in. So, how effective are these IR cameras in measuring temperatures in liquids? In other words, an example would be a vaccine.
Unfortunately, most liquids are not transparent to infrared. They're opaque. So unless you're interested in the surface temperature of the liquid,
Should I change to get better IR pictures, or should I use the 30-millimeter IR lens?
If they're blurry, that means you're not in focus. So what I would recommend is finding where the focus is of your camera. Keep pulling, get to as close a focus as you think it is, and then keep pulling back until the camera is in focus. Without knowing the size of your component, it's hard to tell you which lens is appropriate for you. But I would always make certain. Now, the other question is, if your target is like not powered when you're focusing, we make software, whether it's FLIR tools, the new FLIR tools, where if you're looking at a target that's not powered on, so you're going to get an image that there's not much thermal definition, so in that regard, it's pretty hard to take a focus. What you can do is you can put an area max tool on your image and then slightly adjust the focus and watch the temperature in the max tool. And as it goes up, you're getting closer to true focus. And then once it peaks, and then once it goes over the peak and the temperature starts going down, you back the focus up once, so to the last setting, and that's where true focus is.
Okay.
Again, if you have any questions, send them to sales@transcat.com, and I'm sure the people at Transcat will get myself or another FLIR, technical resource that can help you out with the focus issues.
I'm going to do one more question, and then just as a reminder, well, Ed just reiterated, any questions you can send to me at nvanwert@transcat.com or our sales team at sales@transcat.com, and we'll try to answer those. So our last question today, is the i7 a good all-around camera for diagnostics?
The i7 has 19,200 pixels, so it's a very good all-purpose camera. It stores a thermal image, and it oversees weatherization organizations and has made minimum specifications available, which the i7 meets. It's a very good camera. It stores thermal images on it. If you're looking for cameras with a little more horsepower, the E6 at about $500 more incorporates the visual light image on it in conjunction with the thermal, and also has our MSX technology on it. So again, contact your Transcat salesperson, and we can work with you to select the right camera for your application and budget.
I'm going to squeeze one more question in here because I think
sure.
Because there's beer involved. And I thought that was funny. I think it's beer. They said, what would be the cost, or what would be the best camera or the cost